Alright, for this presentation we're looking at the flying wild scenario. For this scenario we just checked out with the Flying Club on their twin engine aircraft. For this scenario I just picked a light twin, so we'll be using a 1975 Piper Aztec. We're going to be taking a flight into the wilderness by myself. Don't have a lot of experience in twins, and I haven't flown this plane before, so kind of a risky flight, but we're going to be taking it anyways. I'm going to be reviewing some performance charts as well as single engine operations. Some information on the airport that we chose Hot Springs Airport in Virginia. This is an airport that actually is in my area of responsibility at Washington Center. Desirable because it's one of the highest, if not the highest, airport on the East Coast or east of the Mississippi. It's got a chart altitude of 3,793 feet airport elevation. Runway 7 and 25. That is 5,600 feet long, and sits atop a mountain ridge surrounded by mountains, hills, valleys, known for being a trickier area and airport to fly into. Like I said, we're doing a 1975 Piper Aztec. We'll be doing a Lycoming IO 540 engine instead of the turbocharged, just to make it a little bit more interesting. So the first chart we're going to be looking at here is single engine climb performance. So we're going to use, since it's summer day, we'll go 25 degrees Celsius, and we'll just use the altitude of the airport, which is just under 4,000 feet, like we said. So by bringing up 25 up to there, we're barely just inside that line underneath the 4,000 feet of pressure altitude. By bringing that over to the right and following the curve at 4,800 pounds, which we'll use as a standard number there, and then bring it all the way over to the right, we can expect a rate of climb of about 120 around feet per minute climb. That's not great, considering if we go just above the airport elevation at that pressure altitude, if we lose our engine with considering that outside air temp, we're not going to be able to climb at all. Maybe best case scenario, we keep it level flight. So we're just barely in the envelope there as far as being able to just get a slight rate of climb, but again, not really ideal. Probably would make me want to reconsider landing at this airport. Next, look at the single engine service ceiling. So let me get that pulled up really quick. So for that, we'll do the same thing. We'll go 20 degrees Celsius, and we'll go up to 4,800 pounds. I'm sorry, 25 degrees Celsius up to 4,800 pounds, and we're actually just outside the envelope there. Well, let's say, for the sake of argument, we're just kind of right on the edge there, and then we ride it all the way over to the left. So the service ceiling single engine is going to be only about a little over 6,000 feet. That's really not a lot of room to play with, especially considering that, assuming we're doing this flight VFR, but the MIA in that area, I know from working it, is right on the edge of 6,000 and 6,100 feet. So we're barely above the MIA there for the airport itself. Both these aren't looking too good for actually completing the flight. In this aircraft specifically, when it comes to if we do have an engine failure and we have to do it single engine, but we'll keep continuing here. For this final performance chart, we're looking at the accelerate stop distance. So this is basically going to be the distance that we need to stop if we were to actually land there and try to take back off. So looking at 25 degrees Celsius, Coming up to the 4,000 line, just barely on the line there. Okay, so we bring that over to the right, followed the angle down to 4,800, bring that straight over to the right. We'll just assume 0-degree slope, and we said we're going to do it with no wind. So accelerate stop distance is around 2,400 feet. So we said that the aircraft itself, or I'm sorry, the airport itself was, let me double check here, 5,600 feet. So that's enough for us to use about half the runway and be able to have the other half to stop for taking off. Obviously, density altitude considering, you know, before we roll, it could be even further than that, but that is a doable stop if we do have an engine failure on takeoff. Still not really ideal. That is a pretty long distance, and being that this airport is on a ridge itself, there's not really a long or anywhere to really go other than down the mountain if you can't stop on the runway. So you know, obviously these charts too, they bring into account very ideal conditions and ideal condition of the aircraft itself and the braking system, and also noticing the engine failure right away. So all in all, these three charts don't really give a great indication of wanting to complete the flight, but we're going to keep going along here. So talking more just about flying single engine, let's talk about the aerodynamic changes. Obviously, we couldn't discuss this before. You get a much decreased amount of lift on the side where you lose the engine, and increased lift, or not increased lift, but just a very asymmetrical thrust on the side where the engine is good. This is why we raise the dead 5 degrees into the good engine, raising the bad engine. As far as drag goes, we're going to try to mitigate the drag as much as possible by putting in the aircraft in an ideal configuration. You know, when going from 2 engines to 1 engine, the process roughly is, you know, throttles up, mixtures up. You're going to feel that. You're going to give it a lot of rudder in the direction that is, and your dead foot's going to be the dead engine side. So we're going to want to identify the engine that's dead, start pulling that throttle back, feathering that prop by not windmilling. Windmilling is will create a lot more drag than a dead stick prop. So we feather that prop to make it stop spinning, make sure our gear's up, flaps are up. Like we said, raising the dead, closing the cowl flaps on the bad engine, and putting ourselves in a configuration, also bringing the aircraft back to VYSE, which is going to be our best single engine rate of climb. That's going to help us as much as possible to get that aircraft into a clean configuration to attempt to climb as best we can. When you go, obviously you don't want to dip below VMC, which is going to be your minimum maneuvering altitude, at which below that you could lose rudder control, which could cause a roll. And if we're talking about this airport, we already said we're not going to be much higher than the airport if we do lose an engine to where we'd be able to level flight. We don't really have the altitude to lose to gain that airspeed back, so keeping VMC is very important. When it comes to landing on one engine, big mistake a lot of pilots make is they will come in high and on the airport because they want to make sure that they make it, but you want to just make as normal of a path as possible if you're able. Obviously this airport doesn't look like we're going to be able to, but do that, and you don't want to drop the flaps and the landing gear until you absolutely make sure that you're going to make the airport. In this flight itself, pre-planning is a big part of it. Obviously with what we've planned here, probably wouldn't be doing that flight to this location. We'd find somewhere else to do in this aircraft. Single pilot resource management, that's kind of what we're doing now in aeronautical decision making, to do as much as we can before we ever get in the aircraft to make sure that we'll be able to complete this flight with a limited amount of experience, and especially knowing this aircraft. Good thing that we did a good check beforehand to know that this flight's probably not the best idea.